Good morning. Good morning, everybody. Just get my drawing program ready. And then we will be good to go to continue our discussion on fractions. We have a little more to do, just a little bit, as soon as I have something to write on. All right. Okay. So let's give this title Fractions and Decimals. There is a more efficient way to represent fractions and look at fractions as we move from the leftmost basic intuitive side of understanding. As we move to the right, there are properties and ways to do things that are more efficient, more effective. Using decimal numbers as representations for fractions and mixed numbers is one of those things. So if I just do this by example, well, not first, let me just set this up. So if we just look at integers, we have our hundreds place, hundreds and tens and ones, and then we can go smaller, still based on 10, and have tenths. And then we separate that by our decimal point. And hundredths, and so on, in either direction. Now it's still based on powers of 10. They can just get smaller and smaller as well, past the whole number parts on the left and the right of the decimal point. So let's see what we get with some exercises. One way to, well, the main way for us to convert a fraction to its corresponding decimal representation is by using long division again. So we have these three. So let's have a look. So that's exercise 1412, number 1. We have 5/20ths is what? So we want to look, we're not changing the quantity that it represents, we're changing the representation. So this we saw with our division last time, that the top, well, this is really sort of equivalent to 5 divided by 20. That in certain basic division instructions where I can't even fit the group size in, I just get my fraction that corresponds exactly to the division, saying that these are actually equivalent when I interpret them. So that means that the 5 is going to go inside my house, the 20 is going to go outside my house. Now we haven't done long division that much with multi-digit numbers as the divisors, but 20 is not a bad one. So we won't go crazy with these. So we start by saying 20 goes into 5 0 times. Then I still have something left. I now need to keep going until I don't have a remainder anymore. So I'm going to have my decimal place and then just shift my view, just like we shifted our view from thousands, hundreds, tens, ones, and so on. I'm just going to keep shifting it to the right. And when I do that, the method doesn't change. it says, look at this relative to that position, which then makes it 50, because this is 50 tenths. 20 goes into 50 two times, and I have to keep everything in line there, because it's really 20 goes into 50 tenths, 2/10 of a time, I suppose. So 2 times 20 relative to the position is 40. Now it might bother people to see the decimal point there. If it bothers little Timmy, leave it out for a little bit. We know it's there. As long as it's there in the answer, separating those positions, it's okay. So do whatever makes Timmy comfortable, because this division method allows me to sort of look locally and forget where I am in the larger scheme of things. So it's very convenient for that reason. 20, so then I take that away. So I have 10 left. 20 doesn't go into 10. I need to, because there are many zeros here, right? I'll keep the decimal place. I have another 0 I can bring down whenever I need to. 20 goes into 100 relative to this position 5 times. 5 times 20 is my 100. Take it away. I have nothing left. No remainder. So the decimal version of 5/20 is 0.25, 0.25. Now, yes, there are other ways to do this. You could look at an equivalent fraction and put it over a power of 10, but that's not always going to be so easy to do. In this case, we start with a nice simple example. Long division will always get me there. And then the benefit of having a decimal number instead of a fraction is when I do the arithmetic, it works in the same way with our methods that we've established before when we look at our number system. So it is much more convenient. But you lose some number sense when you start with this. You don't want to start with decimal numbers. Once you're comfortable with fractions, then we move on and see alternative representations and how it fits into the grand scheme of things. Let's try a couple more. 6 over 25. That means 6 goes in the house, 25 outside the house. I pick nice and easy denominators, see? Let me just check if there's any YouTube comments. I don't have it open. People don't comment often, but I have to be ready. All right, 6. 25 doesn't go into 6. 0. Keep my decimal point for positioning purposes. Then I need another 0, which is right there. 25 goes into 60 2 times. 2 times 25 is 50. I, of course, know relative to where I am, it's 50. I say 50, but it's not really 50. It's 50 tenths. Then I have 1 left. Well, really 10 relative to this. I need more zeros. Bring them down. I can look at 100. 25 goes into 100 4 times. 4 times 25 is 100. Relative to that position, I have nothing left. So 6 over 25 is 0.24. Again, you might say, oh, that was easy. Because we pick nice denominators to work with, it isn't terribly difficult, but we don't need it to be terribly difficult to demonstrate the method. Now I lost my last question. Where are you, last question? Let's do a 2b. Just take a super easy one. Because for little Timmy, he might have never seen 1/3, right? He saw it in his intuitive number sense building examples, drawing a rectangle, representing a third, visualizing it, that's all good. But when it comes to decimal version, maybe he's never seen it before. So let's do it. So we put 1 in the house, 3 is the divisor, 3 goes into 1, no, never. 0 times. So I need another 0. Now I can look at 10. 3 goes into 10 3 times. 3 times 3 is 9, of course, relative to where I am. So I have 1 left. Bring down another 0 because my remainder isn't 0 yet. 3 goes into 10 3 times. 3 times 3 is 9. And then you're waiting for little Timmy to say, but wait, this is going to happen every single time. I'm never going to get out of this loop. Every time there's 1 left. Every time it's 3 times. I'll go on forever. Yes, you will. So you see here, there's a repeating section, which means I'm never going to get a remainder of 0. This is going to go on forever. So there are decimal numbers that repeat forever, and we just put a little line over it. Some use a dot, I prefer a line, to indicate that the 3 is repeating forever. So that's the downside, unfortunately, of decimal numbers. They're not as clean as the fractions are. Some of them have decimals that continue forever. It literally never stops. And we will talk about rounding a little bit later. You have to round this number to sometimes work with it, and that could lose some accuracy. So that is the unfortunate downside to decimal numbers. There's a trade-off. I think they're still worth it, even though I have this property. So some fractions are what we call a terminating decimal number. Some are what we call a repeating decimal number. They're both fractions, but really it depends on what the numerator and denominator are. Could result in a terminating decimal, could result in a repeating decimal. But luckily we only get those two. Let's just do one more. This is number 3. 13 over 12. Now let's suppose we want to leave it like this. And instead of converting it to a mixed number first, maybe you don't even want to bother with that. It really doesn't matter what form the original fraction is in. I'm still going to have to divide by 12. 12 goes into 13 once. 1 times 12 is 12. Take it away. I have 1 left. I need some zeros here. So I have, relative to that position, 10. 12 goes into 10 0 times. I haven't done anything yet. Bring down another 0. Now I can look at it as 100. 12 goes into 100 8 times. 8 times 12 is 96. So then I have 4 left. It's not quite enough. Bring down another 0 for 40. 12 goes into 40. How many times? 3 times for 36. 36. And then I have 4 left. Still not 0. Bring down another 0. 40 again. 12 goes into 40 3 times. And then I start to see, ooh, wait a minute. There's my repetition. Every time I get the same remainder, I'm going to get stuck in a loop. Now you can verify a couple of times to be sure. Don't wait for just the first one. Be sure you get it repeatedly. Then you see, it's going to keep going like this forever. So what I actually have here is a repeating decimal number. Even though I might have a couple of 3's in my answer before I'm convinced that it is repeating, only put a line over the first one that is going to be repeated. Alrighty. Now, I don't know how familiar you are with these things. Could be very familiar, could be not at all. I'm going to do a number 4. Let's say 2 over 7. 2 is in the house. 7 is outside the house. Single digit, can't be that hard. 7 goes into 2 0 times. I need more zeros here. 7 goes into 20 2 times for 14. And then I have 6 left. 7 doesn't go into 6, bring down another 0. 7 goes into 60 8 times. 8 times 7 is 56. Of course, all relative to that position. Then I have a 4 left, which hasn't occurred yet. 7 goes into 40, goes into 4. 0 times, bring down a 0 to make it 40. 7 goes into 40 5 times for 35. Then I have 5 left. That hasn't happened yet. Bring down another 0. These arrows help me keep everything in line. It's very useful. 7 goes into 50 7 times. That doesn't sound right. Do I do this right? Sure. I'm just thinking of something else. For 49, that leaves a 1. Bring down another 0 over there. 7 goes into 10 once. 1 times 7 is 7. For 3, 3 hasn't happened yet either. Bring down another 0. 7 goes into 30 4 times for 28. I'm running out of space here. 28 has left 2. It's not 0 yet. Bring down another 0 for 20. 7 goes into 20 2 times. 14. Take it away. 6 left. Ooh, and now I see this has happened over here. It has happened before. So finally, I'm repeating myself. And the next one's going to be an 8, 5, 7, 1, 4, and so on. So it does repeat, and a lot of it repeats, a large section. All of this repeats over and over and over and over forever. So a repeating decimal doesn't have to have just one digit repeating. It can have 2, 3, 4, many. This one has 6 of them repeating over and over and over and over and over. Still a repeating decimal. So it's really, in some cases, I have to be patient and wait, see. If it comes from a fraction, it's going to either terminate or repeat. And it's just a matter of how big is that repeating section. Could be longer than just a couple of digits. And I have to just be patient to wait for it. Assuming, of course, I've done all my little divisions correctly. To make sure that at every step I've done it right, so that a single digit here isn't unfortunately wrong, then my pattern will get all messed up. So I have to be sure of all my multiplication tables, which is really what I'm using here. Okay, so that is one side of the coin. Which is from a fraction converted to its corresponding decimal representation. The other side is also there. If I'm given a decimal number, what is the fraction or mixed number that it comes from? Now, in some cases, that question is quite straightforward. Let's look at exercise 1413, and I'll just copy it down for us here. Number 1 is 0.378. In the case of a terminating decimal, this other direction, we've done the first one, right? This other direction is really not difficult, to the point where you almost don't have to say anything. If you understand what these decimal places mean, then the answer is quite straightforward. Let's suppose this way. 0.3 would be 3/10, because that's exactly what that decimal place means. 0.37 would mean 37/100ths. So 0.378, as our example, is 378 over 1,000, because it stops in the thousands position. This is just a side note. So it's really as simple as just putting it over the appropriate power of 10. Let's look at number 2. It doesn't matter how late that is. That 8 is in the hundredths position. It's 8/100ths. .95 is our next one. I don't care about the 5. I care about the decimal portion. I think almost it's better to do it this way, especially for what's coming up. This is just a 5, and 0.95 is 95 over 100. And I can then put it back into a mixed number, which is perhaps a more intuitive version. Or, of course, you could have gone 595 over 100 and have it as an improper fraction, whatever makes you happy. So, in the case where my fraction is, or my decimal rather, is a terminating decimal, there shouldn't be any problem. However, when it's a repeating decimal, we have an opportunity to see something interesting that leads us into the next topic very nicely. I'm just going to pick a simple one, like let's just pick this 0.95, just randomly. 0.95 equals what? Let's suppose, just for a moment, I didn't know what to do here. I can do this in a much, much fancier way. Admittedly, I don't need it here, but for what's coming up, I kind of do. What is another way that I can structure this and have it look much more mathy? I could say, let's give this a name. Let's give the decimal representation a name. Well, I have a question mark here. Let's just make it a more interesting question mark. Let's say question mark in a box. That is my symbol that I'm going to use to represent this decimal. It's going to be the fraction version that's hiding out there. It's hiding behind that. Imagine I can peel this back like a sticker and it would show the fraction. But the sticker is there. I can't see the fraction. My goal is to figure out what is that fraction, pretending this is much more complicated than this specific one is. Okay? Well, what we can say then is, look, this is messing me up. The fact that this is a decimal number, it's messing me up. So let's just realize that, okay, this question mark in a box equals, it has the same value as 0.95. It's the same thing. Equal means it's the same thing. And I chose this symbol to mean exactly the same thing. So I haven't really said much. I've just sort of rephrased this this represent word into my mathematical word, which is the equal sign. That's all I've really done. Now I want to think of equations and what they really mean. They really are representing things that are in balance. So in the old days, you had these balance scales that people used to balance and see more than something else. If you put stuff on either side and it tips to that side is heavier. That side has more stuff, assuming all things are equal. If the scale remains in balance, then the two sides are equal. So right now I have an equal, so the question mark in a box and the 0.95 are perfectly in balance. If I now put two of them, I put another question mark in a box on the left side. I'm going to have to put another 0.95 on the right, and then everything will be in balance again. So if I duplicate it in the same way, everything's going to stay in balance because the original pieces were the same. So if I do 10 of these on the left, as long as I do 10 of these on the right, everything's going to be in balance. But now I want to pick an amount that gets me to not look at this decimal point. So what I'm going to do is I'm going to multiply each one by 100. I'm going to have 100 copies of the question mark. Then I better have 100 copies of 0.95 as well. Then everything will still be equal. So as long as I do it on the same side, as long as I do the same thing on either side, everything's in balance. So now I don't know what 100 question marks will be so far. So I'm just going to write 100 question marks is what I have on the left. Don't know what that is yet, right? But it is equivalent to, now what happens if I multiply a decimal number by a power of 10? Every time I multiply by 10, I move the decimal to the right. So because 100 has two zeros, 10 times 10, it's multiplying by 10 and then multiplying by another 10. So really, this is equivalent to 95. I can take smaller decimal examples to convince you that multiplying by 10 is just shifting the decimal point around. So the reason I took 100 was that I didn't want to look at this uncomfortable for me decimal point. Now there's no decimal point in there. And I just have my more familiar integers. Oh, it's 100. Oh, it's 95. Great. Okay. So now, and again, I'm assuming either you're not super comfortable with this, which is totally fine, or I'm thinking of this as from a teaching perspective. For someone that's never seen these things, never thought about balancing, never thought about equations, never thought about anything, I need to say it in a simple way that every little step I make doesn't feel like a big jump. So they can say, okay, I'll just put an equal sign there. It's still the same thing. Okay, I can picture the balance scale. Okay, I'm multiplying it by 100. That's why they're still in balance. It's the same. Okay, the decimal point shifts. So every little step I make is no single one is overwhelming. Yet we're stringing them all together to get to where we want to go. We want to make sure that no single line is a jump. That's too big for your audience. And I'm thinking of my audience being little Timmy seeing this for the first time. I know where he needs to go. He's going to soon have to handle repeating decimals. This is going to help him. Right now, I'm taking a fraction that I know what the answer is and seeing how I can do it in a fancier way. And that fancier way becomes necessary soon. Right. So now, again, it depends on your audience. I'm going to go as basic as I can here. I have a multiplication sentence. Mathematical multiplication sentence. And he would have done that without the symbol. He would have done multiplication sentences. He would have done, for example, 2 times 3 equals 6. Look at the workbooks. They take this and they write it in all 4 of its versions. The other version is 3 times 2 equals 6. The other version is the 2 corresponding division sentences. 6 divided by 2 equals 3. 6 divided by 3 equals 2. Those 4 go together. And they take one, whichever one, and they have to write the other 3. as exercises over and over and over. Grade 3 should be around grade 3 as they start learning their multiplication tables and their connection between multiplication and division. You always have these 4 sentences that go together by just shuffling things around. So a certain combination might be a multiplication. Shuffling them around has a corresponding division. So now think of this sentence as this first one, where instead of a 2, I have 100. Instead of a 3, I have a question mark in a box. Instead of a 6, I have a 95. There's still a multiplication sentence that can be rewritten as a division sentence. And I want the division sentence that leaves the 3 on its own. It's this one. So I have my division sentence. If I just match this, 6 has the role of 95 divided by 2 has the role of 100 equals 3 has the role of question mark in a box. This is one of my division sentences, and because I'm trying to figure out the question mark in a box, I want that guy alone on one side. Now if the left side balances the right side, then the right side balances the left side, so it really doesn't matter which way you write it. I'm just going to turn it around because I like my symbol on the left. And then the only thing that is left is to realize that division is just an instruction for a fraction, the instruction version of the fraction. So I can go back to the start and say I've now figured out that 0.95 is 95 over 100. Now, of course, we knew that because we had an easy enough fraction to just understand decimal place values. So this was complete overkill. But when it comes to repeating decimals, this is the method. Because there, the decimal never ends, so I can't use powers of 10. It just doesn't work. So I need a fancier method, and this is going to be it. So I take an easy example, which I already know the answer, and see that this more elaborate, sophisticated method still works, and I can trust it moving forward. So it's very important to be able to defend what you do. Even though the student might not know what's coming up, you do, and there is a level of trust required. But at least I can defend it and say, look, Timmy, I know what's coming up, and we're going to need this. So while it's not too difficult a decimal number, let's focus on the method that we'll need moving forward. And let's use it on number 4. Now I have a repeating decimal number. Now I know all repeating decimal numbers have fraction representations. I just have to find it. This is going to be my method. And it's not something I made up. This is the method. I'm going to use whatever symbol I want. I'm going to use question mark in a box because it makes me feel comfortable. I'm going to let that represent the decimal number that I am working with. So I just have an equation then. If I translate this fully to a mathematical sentence, meaning an equation, I just have an equal sign there. So these two things are equivalent. Put them on either side of a scale, they're perfectly balanced. Behind this question mark in a box sticker is the fraction I'm trying to find. However, I can scratch this corner as much as I want to. It's not going to peel back, but it's there. Now it's a little different in terms of the decimal number I have here, in that the 4s never stop. They never stop. I'm simply going to move the decimal number, move the decimal point to a position that steps around one of these repetitions. And because 4 is the only thing that repeats, I'm going to multiply by 10. So let's say here next, 10 times question mark in a box. I need to multiply 10 on both sides so that the balance scale is still level. If I multiply the right-hand side by 10 as well, I move the decimal place 1 to the side, to the right. And what I have is 4, and then still infinitely many 4s. They never end. I never run out of 4s on the right. The line simply means they are there forever. So if I move the decimal place once, there are still infinitely many 4s following it. But writing a bunch of them with dots is not very precise and clean. So we use the little line. Okay. So the first thing I have to be happy with is that when I multiply a repeating decimal by 10 in this case, it moves one of those forward to the ones position essentially, and then still have infinitely many repeating. Everything is still in balance. I know that's a sticky point for some. All right. Now, the problem is, contrary to what I had previously, that was enough for me to not see a decimal number anymore because it was terminating. Here, unfortunately, my goal is the same. I don't want to see a decimal number. I don't know what to do with them. I know what to do with whole numbers, with integers. This one, still a decimal number. Huh. So if I think about the balance scale again, I have some stuff over here. I have some blocks or whatever. I have some blocks over here. If this is in balance, and I take, let's suppose all these blocks are identical. I take one of these blocks away, and I take one of these blocks away. Everything's still going to be balanced because I took the exact same amount on both sides. Everything's balanced. So that means if I subtract the same thing on either side, then the equal sign is still good. Everything is still in balance. The equal sign means balance. Now I'm going to just go to the right side first. What I want to take away is 0.4 repeating, because that is exactly the decimal tail here that I don't want. I can subtract anything I want. I want to subtract whatever the decimal portion is, which is 0.4 repeating. So that then, I'm just going to skip ahead a little bit, I'll have just a 4. I'm trying to get away from decimal numbers. I'm always, if you look at a common theme throughout what we're doing, we're always trying to relate things back to what is more familiar. When we look at fractions, we relate it back to an integer calculation because that's more familiar. When we look at a decimal conversion here, we're relating it back to integers because they're more familiar. However, I have to make sure that I do the same thing on either side. So I need to subtract by the same thing on the left as well. However, it's a little bit of an apples and oranges situation on the left. On the right, I was sort of speaking the same language. If there was a decimal number, I take away a decimal stuff. They understood what I wanted to do. Here, originally on the left, they have a bunch of question marks. Now I come in and want to take out a decimal number. They're going to tell me, no, I don't know what to do. you're right in that you need to subtract the same thing, but you're not speaking our language right now. We don't understand what you want us to do. Then I come back and say, well, my question mark in a box is exactly the same as point 4 repeating. These two things are equivalent. So instead of me saying, I'm just speaking the wrong language here. Instead of me saying take away a point 4 repeating, I can say take away a question mark in a box because they are the same. They're the same thing. It's like one is your formal name and one is your nickname that your friends gave you. If you go to your, well, maybe not your friends, yeah, sometimes. If you go to your friends and someone addresses you in your uh, official name on your birth certificate, some of their friends might not know who that is because they only know you by your nickname, maybe. It happens. But if you refer, if your friend, if another friend refers to you by your nickname, oh, then that friend's gonna know who's being referred to. It's still you either way. It's just a matter of which name should be used for the group the group you're in, which side you're on. Still the same thing. And I have to subtract the same thing. So now on the left here, now they say, oh, you want to take away a question mark. Well, we have 10 of them. If you take away one of them, we'll have left 9 of them. I know you don't need the multiplication sign there, but that's nice. All right. So we have gotten to a point where we don't see any decimal numbers anymore. Phew, that's nice. Now again, multiplication sentence that if we use numbers, that's not strange to anyone. There are 4 of them. I'm looking for a division sentence that corresponds to this, but of course, I like my question mark alone on one side. It's going to be 4 divided by 9. You can't tell little Timmy, oh, divide on both sides of the equation. He's going to look at you like, what? I'm not doing algebra. I'm not in high school. I have no idea what you're talking about. But if you talk about multiplication sentences and equivalent division sentences, they've done this since grade 3. Put it in a language that he can relate to. And so, question mark in a box is 4 over 9. Go up here. Remember, your understanding might not be at the right level for little Timmy. You need to rephrase all these things. And we can easily. Easily. Yes, I'm working with equations. Yes, I'm working with a variable. Don't use those words. He doesn't know what that means. He's grade 3. Well, not grade 3 here. Grade 4, probably 5 these days. He hasn't done algebra yet. He hasn't even heard the word algebra. You can still do it. The concepts are the same. Logically, it's all the same. Sorry, I missed a YouTube comment here. Do you only put the line over the repeating numbers? Like 3 on the last question. Sorry, I'm very late to that comment. I don't know where you are. Whatever is repeating, yes, maybe this one you mean? The 8 never repeats again when you do the division. The 0 doesn't repeat either. You get into a loop and the 3's keep coming up. So only the repeating portion gets a line. Otherwise, it doesn't mean the same thing. If I were to say 1.083 with a line, that would mean 1.083083083, and that section repeats forever, and that's not the same anymore. Yeah. Sorry, I'm not used to people commenting in YouTube. It's so rare, actually ever, anywhere. Everyone's super quiet. I've gotten used to just talking to myself, which is unfortunate, but true. So, See the similarities here? I handle them different. I do see them differently. I handle a terminating decimal in a much more convenient way because it's not as complicated. I don't need all this fanciness. I just don't need it. You can do it, but it's a too fancy a tool for the job. But when I have a repeating decimal number, well, that's a fancier job, and it requires a fancier tool. And I want to do that in a way that is not just for me. If it was just for me and I have enough experience, I could probably guess and check my way through this. But for me to understand why this is 4 over 9, for me to potentially teach this, I need to have a logical argument that systematically gets me there with each step, not a big jump. That's how we do it. That's how you pass on knowledge. That's how you make someone else better. Honestly, that's how I make myself better because now I understand it better as well. Yes, if I've seen uh, this kind of decimal a lot, I start to recognize it's over 9. Zero point 0.6 repeating, 6 over 9. Sure, there are a lot of patterns here that with enough experience, I can use that. Sure, but I pretend I have no experience. I need to figure out. I need to figure it out. How do I do that? You can't tell little Timmy, it's 4 over 9 because that's why I say it's what I say it is. Just accept it. No, no. That's how we get the vast population not having any idea about any math and scared to death of it because their teachers just forced patterns on them that they don't even see. That's not how it works. Just because people do it doesn't mean it's right. So now I see the 7 and the 2 repeating. That dot is it's not supposed to be there. So 2.72727272. First thing I want to do here is get rid of that whole number portion. I do not care about it. It's going to mess me up. Never ever use it in your argument because I don't need to. The 2 is not an issue. The repeating decimal is the issue. Get that 2 out of there. Sometimes it works perfectly and it won't mess me up. Sometimes it's just going to make this unnecessarily complicated. Never ever use it because I never ever need to. That's the first thing. So now I'm going to say, maybe I don't want question mark in a box. Maybe I want a little star to, whoops, I don't want to say it like that, to represent, bad habit, represent what I need it to represent. Then mathematically speaking, those two things are equal. Okay. I want to peel back this star sticker to see what is the fraction. And then once I see that fraction, I'll put it here and put it with the 2 and make a mixed number. I don't need that 2 in this argument. I only need to focus on the decimal portion. All right. So now I'm going to have to, I'm always doing the same thing in that I want to get the decimal point past the repeating section. And this time, 2 decimals are repeating. Oh, I just saw we're already out of time. I think we're going to have to pause here. I'll just do one more. So this time I'm going to multiply it by 100 because I need to move the decimal point twice so that I get 72, the repeating section, out. But of course, there are infinitely many 72, 72, 72s repeating. So there's still infinitely many of them after the first 72. They never end. And on the other side here, of course, I have 100 of these stars. So unfortunately, this is where we have to pause. But if you want to, think about what would we do next? Matching it with the, where's the 4 over 9? There it is. Matching it with what we did here. Same argument. What would I do next? Can you finish it? And of course, I'll make a note. Remind me if I forget. We're at number 5. And we'll just take as long as we take. Because this is a step up in sophistication of an argument. It's not something we are necessarily comfortable with, which means we need to take our time. We need to slowly do one step at a time, because if I understand each step, going from this step to this step, this step to this step, this step to this step, okay, that makes sense. Okay, one more step. Then when I look back, I've done the whole thing. No single step should be an issue. When I string them together, I've actually done a whole bunch. But it takes time. It takes time. So think about this if you want to. It's okay if you don't. But unfortunately, we're out of time here. Are there any questions before we pause this discussion? All right. Until next time, then. Thank you. welcome. I wasn't sure anyone was going to show up. Let me just open all the things I need to open, do all the things I need to do. This one. Okay, good. All right, 1 second here. All right, let's do this. So for today, we are just practicing some substitution. We can go back and do just easier indefinite integrals, but let's mix it up. And when we look at, for example, problem 2.4, we'll see they might be mixed up, although most of them, they might be a little bit more mixed up. So let's focus on 12.4. If you have one you would like to do, please say and we'll do that. Otherwise, I am just going to randomly do them. I'll just start at the beginning. Have we done this one? It looks so familiar. Don't know if we've done it. We'll just do it again. Feel free to interrupt and ask questions and do what you need to do. So, we are going to do the integral of this guy. Now, again, I might be repeating myself, but that's okay. When we looked at the chain rule and we wanted to find the derivative using the chain rule among other things, in the beginning we used the u and we defined it according to the inside function that we wanted and so on. And eventually, as we got more comfortable with the chain rule, we stopped doing that. And we just said, oh, the inside something to the power of 3 and blah, blah, blah. When it comes to substitution, I don't really want to do that. I am always going to write the 3 lines. Let, then, so. And it's not going to ever be a case where eventually I'm going to let this go. No, that's not going to happen. I have done countless of these, countless number of these. I will still write the u explicitly. In this case, it's obviously 2x squared plus 3, because nothing else is going to allow me to get rid of all the x's. Once I have that, I take the derivative to see, oh, I need a 4x. Aha, look at that, 4x. Separate the differentials as my key for what I need. And I see I have everything set up perfectly, no adjustment necessary. It's going to be 1 over u cubed du, because those two, 4x and dx, are exactly what I need to see to sub that for a du, and the rest is, of course, my inside function. Then, I can see this if you want to, u to the negative 3, if that makes you feel better. The antiderivative, or the main antiderivative of u to the negative 3 is then going to be u to the negative 2, and I need a negative 1/2 in front to balance what the power rule is going to do with target in mind. Then, another long line here, I simply have to go back to x's. And I put in, I don't change anything, but put in what u represents in terms of x. Again, if you feel like simplifying this further, you have a burning desire to do so, go right ahead. I do not have that desire. My simplification desires are based on practical necessity. Am I using this answer further? Do I have a need to clean it up before moving on? No, so I won't. So once we get the hang of it, it's quite straightforward. The recipe tells me what to do, tells me what to look for. Don't not write these 3 lines ever. Always have them, always. Yes, technically this is the chain rule in reverse, I guess, but not quite. It's not the same. Similar, it's not the same. So it's the same level, but I don't have the convenience of dropping that full substitution written out. It's not gonna become easier if I do that. All right, good. No, that was an easy one. I'm not gonna show the question every time, but I do have 12.4 in front of me. I'll skip one if I feel like it, but the next one's a good one. Integral of root 1 minus x. It's a good one. I like it. So I clearly see a function of a function. Whether there is something else around it that I may or may not need, it's kind of irrelevant. I have one tool, it's substitution. My life is actually quite easy compared to other calculus courses that have other tools that may apply in more complicated situations. I have one tool, it's substitution. If I see a function of a function, substitution is the only thing I can do. So if it doesn't work, then I might have made a little mistake, or the problem just can't be done with substitution. I don't have any other options. So it's actually quite straightforward. So I choose the obvious inside function. Then I'm going to take the derivative, which is quite nice and simple. And so I separate the differentials like so. Always 3 things that I write down. Now I have to modify the look of my integral according to what I wrote down on the right here. Alright, let's do this. Well, this says that the root's going to be okay. It's going to be the root of u. No problem. In order for me to bring in the corresponding differential, I need a negative, and a dx. See the dx, I don't see the negative. So I will balance that with a couple of negatives, because they will cancel each other and give me the same answer as before. So the first negative out there is just the price I pay to bring in this negative. Now I have the root u and the du, because the negative dx becomes du. I don't like the look of this. I prefer to see the exponent for my power rule. I will go ahead and rewrite it because I need to. Antiderivative of u to the 1/2 is going to be u to the 3/2 basically. But there's no constant in front, so I'm going to have to put a 2/3 in front to catch what the power rule is going to do. And then I am essentially done. But the u was my choice. You could have called it something else. I chose to call it a u to help me My end answer can't rely on that. So I just swap it back. Like so. Let's see. No problem. I hope. Now I don't quite see the modified version of this. Maybe later on. Maybe number 10 is a modified version. But let's actually do the modified version right now. Because what if I forget? Let's just do this guy. I may have done this before. I really don't remember. They all blur together at the end. I see a function of a function. Yes, I see other things. It doesn't really affect my starting attempt. Don't have much choice. I have a function of a function. It's not much choice here. I have one tool and I'm going to have to try it. So everything looks similar on the right. Good. Now I see the same problem with the negative that I need with the dx. I don't have a negative, so at the very least, let's fix that. The root is going to be okay. I don't know about the x yet, so one thing at a time. I need to fix that negative, right? So these guys will become du. The root will become root u. And then I still have this x. That's a bit of a pickle. Because for this to work, I'm supposed to rewrite the whole thing. So this is not right. But luckily, I can go back here and look at my substitution, which is really giving me a relationship between the u variable and the x variable. That sure, I ideally use it in this way, but I can also use it in the other way by just solving for x. Still the same thing. That's what I'm going to do here. Now for a more complicated substitution, it really isn't very viable. But because my substitution is simple, linear, swapping them back and forth is very easy and not going to run me into any problems. So there I go. Everything's in U. I wasn't concerned about this x in the beginning. It'll all work out in the end, if I do everything right. Now I have my negative here. I don't know what to do with this. Product rule? No. There is a product rule for integration, but that's way too hard for us, in my opinion. So I'm going to have to simplify. Multiply the root u in. Then I'll do this for now, which is correct. But in terms of using the power rule, maybe not ideal. So go to my fraction powers. It'll be u to the 3 over 2. Remember, the integral sign and the differential act as brackets. So though you can have brackets here if you want to, you don't technically need them. They do look nice though. I prefer them. Regardless, antiderivative of u to the 1/2. We've just done that, I think. U to the 3 over 2 with a 2/3 correction. There are no extra constants here in front. U to the 3 over 2. Antiderivative is going to be 5 over 2 2/5 correction. Remember your C. And let's squeeze in my last step, which is a formality using the substitution back to x. U is 1 minus x. I don't care about the root version or the exponential version. I don't care. to simplify this. Simplification is subjective. It's based on my needs, and I have no need because it's my final answer. How do we feel about that? There are about 6 people listening. 7! Woo! It's a new high score. 7 people are listening. How do you feel about this answer? You should have an opinion. Because what if this is the exact one in the test? Then what do you do? Would you do this? Would you be happy with this answer? We will do more exponential fractions, sure. But first, this one. Let's just double check this one. Obviously, I'm hanging around this question because it is not right. It is not right. Why not? It looks so good. Where could it have gone wrong? Where? If you don't know, that means you run the risk of doing this exact thing, which is extremely likely, and I see it all the time, because people do not pay attention to their brackets. If there is one thing I can label as a common mistake throughout every semester, it's inconsiderate bracket using. You don't pay attention to your brackets when they alter the meaning of things. Whether I have brackets here, I actually put brackets in for you, showing this negative applies to the whole thing. Whether there were brackets there or not, the integral sign and the differential act as brackets. So the negative is waiting to apply to everything. Yet that's not what I did. I applied this negative to the first one and not the second, because that negative is that negative. But there are 2 negatives for the second one, making it a positive. And then, I subtract 1 mark when this happens, and then, oh no, I'm the bad guy for doing that. How dare I subtract marks, right? But it's not right. And it could indicate a fundamental understanding on your end for how these things work. I have to subtract a mark. But then people complain. I don't think I should have lost that. It's so unfair. Is it? Is it unfair? Really? I don't think so. Mistake is a mistake. Mistake is a mistake. Okay. Go over exponential fractions. But we just did that. What else would you want to do? What problem would you like? Pick a problem. It's really just the arithmetic then, isn't it? I'm guessing. Totally guessing. That if I say something like, it doesn't even matter what I say, right? X to the 7 over 3. Ooh, I like it. Is it hard, or is it just a little unfamiliar? What I'm doing is the power rule in reverse. There is no extra difficulty here. I'm going to go 1 up on my exponent, check the correction, and I'm done. Whoops, that's not a 0, goober. C. It's just a very curly C. There is nothing more to this, if that was your issue. It's really just, I don't see the fraction powers often. So I just have to do the arithmetic carefully. But it's always 1 up, because that's what the power rule is going to require. It's going to bring it down by 1 to give me my target. Not sure what you mean by exponential fractions. That is not quite a term. That means only one thing. But let me know if you have a specific problem in mind you would like me to do, we can do it. We can do it. Now, if I look at number 3, that looks pretty much the same, right? Number 4 is quite boring, I think. Let's review 5, just because. E to the natural exponential function, super important. This would be e to the 2x plus 3. This session is there for you. Ask questions. Say, could we do this number? Yes. I'm just not sure what you mean by exponential fractions. That's weird. I don't know what that means. So let's just do this one until you want to do a specific question. I see a function of a function. And if you don't, that is a problem. Because this comes from the recognition of the issue comes from way back, chain rule. This is just the chain rule in reverse, and it's called substitution. It's my method for making sense of this. What did the chain rule really do? I said it at that stage as well. The chain rule, by breaking it up into 2 parts, allowed me to find the derivative of a composition without ever really thinking of the composition itself. The method of substitution is doing the same thing. I have a composition of function here, or I have a composition of functions here. What the method of substitution allows me to do by rewriting this to, well, I can almost rewrite it. I need a 2 with a dx, and there is no 2. So I'll balance it with a half, so I can bring in a 2 and not change anything. Now, when I rewrite this, what the method of substitution is allowing me to do is to do the chain rule in reverse without me thinking of the chain rule in reverse. That's complicated. I don't want to do that. Ew. So it says, no, relax. Don't worry about it. Don't think about the chain rule. Let's just rewrite it. And then, look at that. There's no chain rule. Don't worry. Just do this. Can you do the derivative, the antiderivative of e to the variable? Just the variable? Yes, I can. No chain rule. Relax. Deep cleansing breaths. And now let's just get rid of this u and go back to my original variable. Can you do a substitution? Sure I can. And there you go. You've done the chain rule in reverse without actually thinking about the chain rule. See? And you're happy, and you never had to worry about it. Because the chain rule and compositions of functions are really complicated. They're the most complicated way of combining functions by far. So when we're talking about derivatives and antiderivatives and all kinds of stuff, that's hard to combine those 2 things. We have these methods, chain rule on one side, substitution on the other, to allow me to break it up into pieces and not be concerned about what I'm actually doing. Do little steps and then look back and you've actually done the whole thing. It's nice. It's very nice. Without substitution, I really only have guessing and checking, and in this case I can guess and check my way through this one, sure. But for more complicated ones, that is a recipe for disaster. More questions? Okay, you found one. Good. 12.3.5. I don't even know what you are talking about here. 12.3. Oh, right, got it. I'm slow. 12.3, number 5. I'm hoping that's what you mean. Isn't this one? Yes, okay. I, for a second, thought you were looking at a different book, and I'm not really interested to open Friday. I'm lazy. Plus, I have my own book. 12.3.5, you say. Why not? This session is there for you. Someone else should pick some questions as well. And if you have no issues and no questions, I find that unlikely, but I guess it's possible. Great. But if you have any issues, any doubts, this is what we're doing. Though I do just enjoy doing it for fun. Kind of more here for you. First thing, I should obviously see, well, I have a function of a function. There's no way around it. There's the chain rule is at play here, but antiderivative, so substitution. The obvious choice is the inside function inside the square root. But in the case where the choice for inside function is less obvious, just try one. If I'm able to rewrite it in terms of u, it was a good one. There are rarely much choice in this kind of question, for us at least. Separate the differentials. This one is quite straightforward in that I see the 3 that I need to see. It's beautiful. I don't even have to make an adjustment. So I'm ready to replace everything that has an x in it. 1 over the root of u. 3dx du. I don't like my du in the numerator, though there's nothing wrong writing it like that. I just don't like it. Because at this level, I want to see the container of the function. I think that means more visually. It's nice and little reminders subconsciously. I don't love the look of this. I'm going to go u to the negative 1/2 because I know the power rule is what I'm focusing on here. Let us do it. Well, it's going to be u to the something. The power rule is going to bring it down to negative 1/2, so I'm going to have to go up to positive 1/2. But then when the power rule applies to this, it's going to bring the 1/2 in front, but I should have nothing. Well, I have a 1 there, nothing else there, so I put a 2 there to balance what the power rule is going to do when I test it. Then I simply replace back, not changing a thing. If you want to simplify, simplify afterwards or before, not when you replace. Piece of cake. Well, it can be a piece of cake if you go and buy cake or make a cake or do enough of these. It really becomes quite straightforward. It doesn't feel like it is when you're sort of at the beginning. You think, like anything, right? If I've never played piano and I want to go learn piano, if I sit in front of something that's too complicated for me, it seems impossible. I will never be able to do it. But if you take the right steps to build up your skill and knowledge, one day that is very possible and actually super easy. Nothing is different here. If you found that, ooh, I didn't pay enough attention when we did derivatives. Yes, this is super hard. Maybe impossible. But if we build it up through the course, by the time we get to this, oh, it's actually not hard at all. Or it shouldn't be. Might just take time. I might still need a lot of practice, but it's nothing that I can't overcome. It's the same with anything that you learn or see for the first time. Now we're getting some speed here. 12.4, number 8. I like it. Yeah, you should pick which ones to do. I shouldn't pick. I don't know what you need. You're right. I like it. There it is. I will copy it. And we will do it. And I'll just say again, while I'm doing this copying, if you can comfortably handle all of the problem book questions, there is nothing to worry about. The problem book has all the questions, excuse me, all the questions I could possibly think of. A little variation shouldn't trip you up. All right. Do I see a function of a function? Well, yeah, because of the brackets, right? But is the inside function the bracket or the exponent? I don't know, perhaps. Maybe in the heat of the moment, you say, let's go for the bracket. The nice thing about substitution is it's going to show you right away if it's not going to work. It's not even a question. It'll point it out. You just need to listen. Okay, so I wrote my 3 lines. I know the bracket will become a u according to this. This last step says I can bring in a du if you have a negative and a dx. Okay, I'm not worried about the negative. I can bring that in. The problem is, what on earth do I do with this? That's not obvious. Look at my substitution and look at that. There's nothing here that really shows me how to easily do that. So I'm sort of stuck and I need to get all the x's out. So that then tells me, nope, that wasn't the way to go. Let's back it up. Back it up, back it up, back it up. And try something else. And the only other choice is 2x minus x squared. Because that is also an inside function. And by now we should be able to recognize it. Just because it doesn't have brackets doesn't mean anything. All right, now I take the derivative. Derivative 2 minus 2x. Okay, separate the differentials. Now you'd be surprised at how many people do this. Then yet again, I have to subtract the mark because it's not right. It is not right. Brackets are not optional things sometimes. If you don't have brackets there, I subtract the mark, and I am completely justified to do that. People complain, oh no, I think that's so unfair. It looks the same as your answer. I will never not have brackets there. Ever. It will not look the same. You have to have brackets there. And now I see, looking at the first line, okay, this is going to be e to the u. No worries there. Oh, I still have some other stuff here. It doesn't quite look the same, but it does. Factor out a 2, 1 minus x dx. Oh, look at that. Ooh. That simply says I need a 2. Okay, that's not a big deal. Let's do it. Now, many people do it on the first line. I don't want to. Maybe because I just like copying stuff over. But you're welcome to just put it in there. Now everything is in place to say e to the u 2 bracket dx perfect du. Nothing else is there. Antiderivative of e to the variable. Whoops, no, what's that integral sign doing there? I am done with the integral sign because I'm now going to find the antiderivative, e to the u plus c. And then the simple formality of replacing what u is wherever I find it. People also do things like this. I'm just thinking about things, right? Because you came all this way, I don't want you to be one of those people I have to subtract marks for. People do stuff like this. Now, look at this now. Maybe you are trying to say the right thing, but to me, this plus c looks to be in the exponent level. When it shouldn't be. It's on the base level. Because if I have it in the exponent level and take the derivative, then it doesn't go away. So you have to really be careful about everything you are writing. It is the same as every other language. If you are taking an English class and you're writing essays or whatever, and you just have a random word inserted for no reason, or your punctuation isn't correct, what is your teacher going to say? Is your teacher going to say, oh no, it's fine, I know what you meant? Well, maybe if you're in kindergarten, sure. But eventually, no, you can't just miss punctuation. You can't just write things how you feel like writing them because you had the right idea. It's what is on paper that matters. And if it's not correct on paper, technically, you should lose marks. That is just a fact. That is not my opinion. And the nice thing about math and science is if I find something that's wrong, every other math professor will find the same thing. It is not subjective, it is unbiased, it is right or it's not. Simple. How do we feel about this one? What number was this? 8? 8. I try. No, it doesn't, perhaps doesn't apply to you, these little things like brackets and things, right? I'm just mentioning it as it comes up. Because in the background, people are complaining all the time about grading. All the time. This semester more than any other. I'm like, this is math. It's right or it's not. There is no in between here. And if I find something that's wrong, I subtract a mark. Simple. And I don't want that to be you. So be aware everything you write is important. Another thing, for example, other questions, derivative question. Let's suppose my derivative function is whatever. I don't even care. This. Then people say equals derivative of the first. They do the derivative perfectly. Plus the first times the derivative of the second. You've done the derivative perfectly. But this, on paper, is not right. Because what you are saying here is that the function called y, which is equal to this, the function is equal to its derivative. It's not. These two things are not the same. You need to write down the name, the representation, whichever one you want, of the derivative. That is equal to what you were doing. Then people say, but you knew what I meant. No, I don't. I'm looking at this on paper. And on paper, this is not correct. And it could indicate a fundamental lack of understanding between a function and its derivative. -1. That is not a subjective opinion that I have. This is not correct. We have to take responsibility for how we write things. Be careful of every little thing because this is a technical language and everything matters. Now, some people really like that. I love it. Every little thing means something. But it takes a while to get used to that language. Either way, don't hate me when I have to subtract something. Other question 5. I just love ranting. It's so much fun. Now I apologize if this doesn't feel applicable to you, but it's applicable to many because I get a lot of complaints. When grading is grading, it's not up to me. It's not like an essay where the grade you get is very subjective. It's really based on an opinion of the instructor. That's tough. I feel for you in that case. Technical courses, hard science is not like that. Okay, number 5. Whoopsie, what did I just do? I did nothing, it wasn't me. Number 5, 12.4. Ooh, nope, maximize it. That one? Are we supposed to make an antiderivative equal to something in our end answer? Let me go to an answer. We did this one. Where did we do this one? This one. See here, you can't look at now people. This is interesting. I don't know if that's what you meant, but I'm just gonna say it anyway. People look at this and say, "Oh, but you do the same thing in class." No, I don't. It's not the same. Whichever line you had, the next line, because I'm just using an indentation because I don't have space here. And if I don't have anything next to my equal, it means the previous thing is equal to that, which it is. I haven't changed what I'm working on from one line to the next. Then this equal is fine because it means that it's just like a line break. The antiderivative of this is equal to blah blah blah, and your page and your line just keeps going like a normal page would read. I just have a very tight page. So your final answer, if I understand you correctly, is still referring to your original antiderivative question. So if f prime is a derivative and f double prime is a second derivative, what is the equivalent for antiderivative? Oh, this is where we had a new notation. Let's just go with little f. Okay, let's just go with little f, just to make it as relatable as possible. I don't really know why I went big F in the beginning. It doesn't actually matter what I call it, right? I usually start with a function. This is now independent of the question here. I start with a function, call it f, call it y, call it whatever. I have two directions I can go. Before, we went the derivative direction, and we found the derivative. We did increasing, decreasing stuff, whatever you wanted to do with it. We found the second derivative, concavity, and so on. Higher derivatives don't really mean too much for us in graphing, but they have a need in other places. Okay, derivative direction. Or you could say, I have a function, I'm going in the antiderivative direction. Then your representation for the antiderivative, which is really a family, is the indefinite integral. It's not a little adjustment of the name of the function with a prime or a double prime. It's a couple of symbols here wrapping around the function. Now, in higher level courses, you can have a double integral and all kinds of stuff, sort of being the opposite direction, but analogous to the second derivative. There are things like that. We just don't care about them. But we had to come up with a name. I would have loved the little prime notation, but it just doesn't. It's already taken up. Uh, this isn't that inconvenient. Now, it turns out when you do antiderivatives, because it is a little bit more complicated of a direction, because you lose uniqueness and it's messier for sure. Uh, this long S comes from sort of the original idea called the Riemann sum, and I do need to keep track of the variable, just like the little d notation keeps track of a variable. So I guess it's a little bit more appropriate for this versus this. The prime notation I don't love. It's a good introduction notation, but unless things are very straightforward to understand, it's not good because you don't know what the variable is. So now if you have a function of multiple variables and you say, oops, sorry, and you say this, it's not quite clear what you mean. What's the variable? If the x and the w, for example, are equal, not equal, equal standing. One's not a constant. They're actual variables. What do you mean here? I don't know. This is not good to use. But if you say this, then I know, okay, you're focusing on x. Now, this is more complicated to find, but whatever, there are ways. At least your representation is perfectly clear what you want to say. So the prime notation is very much an introduction notation. It shouldn't actually be there. The little d or the big D notation is much better much more complete. And you can then also use, there's nothing wrong with it, sort of a mix between big and little d notation. Say the derivative with respect to x, maybe you want to put square brackets there, and that is then similar to this antiderivative notation. So the derivative notation is actually more appropriate like this. Derivative, variable, function. Antiderivative or integral, variable, function. The prime notation is sort of a lazy man's notation. When I can get away with it, I'm gonna. But if anything is even remotely complicated and I need to emphasize what's happening, prime notation is not for me. That's why there are other notations. Now, the antiderivative, the integral, doesn't even care. It says, look, this is going to be complicated no matter what we do. Let's just list all the things we need to list in our representation from the very beginning. Yeah, it's a lot of little things, a lot of little things. So many, so much more, so much more. But, these things take so long. I sort of, I reviewed high school math recently, and just the amount of time all that algebra takes to develop, to get used to, all those little rules for exponents, for simplification, for factoring of polynomials. It is shocking how much it is and how much time it takes to get comfortable with those things. It bothers me that it takes so long, but it does. You can't accelerate those things. There are so many interesting things. Where's my page now? So many interesting things. But they take such a build up over years to even make sense of what this, for example, is. That you have to have such patience, and it's really hard in school or in pre-calculus. For me, it was very hard to to get a question like, where are we going to use this? Why do I need to learn this? It's a very hard question, one I dread, because we don't have the tools to really show any interesting, fun applications. Only now we can sort of hint at something interesting with optimization. Things get a little bit more interesting because the design of a box, the design of a can, while minimizing the cost, that's an actual legitimate question. When you see a tin of fruit or whatever in the grocery store, that can, someone had to design that can due to specific specifications, minimizing their cost because they have to make hundreds of them. So you start to better see that, oh, these things actually do have a use, but there's such a background, there's such a buildup of knowledge necessary to even get to a hint of an actual real life application that it can be very frustrating. And I understand why it's not fun in high school. It's not fun because you can't do anything with algebra. What do you do with it? It's all silly, made up questions because we're still building up to get you one day maybe to calculus where you can maybe start seeing an application. It's difficult. There's a lot of patience that's required. But all these things are somewhere in many, many applications. Just sadly, applications are much, much more complicated and we just can't handle them. But there's a lot. There's a lot out there that is very interesting and satisfying to work with. But it just takes a long time. I wish it didn't. All right, that is it because we are out of time. Think about things, have patience, just find some joy in going through the motions and finding the right answer. If you want me to check your answers for any of these problems, yeah, send them on. Super easy. I don't have a problem doing it because I know the problem book doesn't have any answers. Super easy for me to check. Don't worry about it. And then we will move on to still antiderivatives integration. just to see what do these things mean. We saw that the a derivative has a graphical interpretation, right? The slope of a tangent line. What does the antiderivative mean? Surely if the derivative means something graphically, the antiderivative should as well. But what could that be and why? So that's where we are going. Also remember your oral test. Good times. Only takes 5 minutes, but then it's one less thing to worry about. Do that. In any case, that is the end for today. Enjoy the weekend. I will see you guys next week. Bye.